All right, today we're going to talk about gases and the mole and how that relates to volume. So if we'll go over to what we're going to do today, we are going to define the term STP. We're going to talk about molar volume. We're going to talk about converting between volume and moles. It's very similar to the last two things that we've done. We're also going to take that idea and move it into other problems that will involve Avogadro's number and molar mass. So all three of these combined should give you a good sense of the same task, just with different values. So real quick, if you do want to pause this and go in and mess around with the gas simulation, you're very welcome to. I tried to put something in here where I was guiding you guys through it, but it didn't quite work. You can mess around with pressure and volume and notice that you might change pressure, volume, temperature of a gas, but unless you add more atoms, it's the only way to add more atoms. If you heat up a gas, you won't actually change the amount of gas that's in there. And we use that to our advantage in something we called molar volume, right? So let's talk about when gases actually do change volume. If you change the temperature, if you make it hot or if you make it cold, I want you to give your own example of heating or cooling a gas and how that changes its volume. Same thing with pressure. If you change the pressure on a gas, how will that change its volume? And also the amount, how will that change its volume? We're going to go in and do some quick calculations and whatnot, but if you do want to pause it here and fill out that table, I encourage you to with your own examples. So, how large is 1 mole of a gas? Exactly. To give this a quantity, since it does change given the temperature and the pressure that it's at, we have to standardize it. And you can see in the picture we have a standard temperature and a standard pressure of 0 degrees Celsius and 101.3 kPa, which is 1 atm, 1 atmosphere. That's really an easier way of putting it. 1 atmosphere is about the pressure at sea level. If you're standing on a beach next to the ocean, you'll be under 1 atmosphere of pressure on an average day. We abbreviate this temperature STP for standard temperature and pressure. And so when you see STP, it immediately tells you something. The gas is at 0 degrees Celsius and it's at 1 atmosphere. And with that, we can start doing some conversions. And the only conversions for now that I'm going to tell you about are at STP anyway. So let's move on. 1 mole of any gas at STP has a volume of 22.4. We call this the molar volume. So if you had a cube that was 22.4 liters, your volume is 1 mole. It's somewhere between, oh, my battery's running low. It's okay, we're going to make it. Anyway, this cubic feet, 22.4, or not cubic feet, excuse me, 22.4 liters. So about 11 pop bottles. That's going to be your molar volume of 1 mole. So we get two conversion factors out of it. We get 1 mole over 22.4 liters and 22.4 liters over 1 mole. What's nice about this is that anytime you can pause the video, finish the slide, and I can move on as fast as I want because you have the option to. So let's take this idea and actually talk about it. So here I have a mole of helium. So I know there's only 1, 2, 3, 4, 8, 9 atoms shown, but we're going to pretend that it's 6.02 times 10 to the 23rd. If there's that many atoms, we're going to take up 22.4 liters. Same thing with 1 mole of ammonia, same thing with 1 mole of oxygen. Well, this also means that I can actually measure these balloons, right? So they're all at STP, they're all 1 mole. They all take up 22.4 liters, but they do have different masses. So we've got helium coming in at 4 grams, ammonia, it's actually 17, it's not 15, and oxygen is 32. But let's use the 22.4. Let's talk about molar volume. I've got this balloon here. It's full of hydrogen gas. How many moles of hydrogen are in the balloon? So what we're going to do is we're going to do a quick fence post. We're going to take 3.5 liters, put it in a fence post. Liters is going to go on bottom. Moles are going to go on top, so I can cross off the liters. And what I'm going to get when I do that is I'm going to get a division problem because these liters are going to cross off. Hiya, hiya, kind of thing. and I'll end up taking 3.5 and dividing 22.4 for a total of 0.16 moles. So this balloon over here has 0.16 moles in there. Now let's take it, and it's also additive, so I can take 4.5 moles of hydrogen and 2.3 moles of oxygen, in other words, in these two balloons here, and add them to the same container. What volume is going to be needed to fill both those in there? Well, I can take 4.5 moles of hydrogen in a conversion factor. This time mole is going to go on the bottom here, and liters are going to go on the top. So you can see now the 22.4 is going to get multiplied. And when I do that, I end up with 101 liters. Notice how moles canceled out, and we're left with liters. Do the same with the oxygen. You have 2.3 moles of oxygen. You end up putting 1 mole on the bottom, 22.4 liters on top. You multiply them, and you get 53 liters. Now, if one takes 101 liters, the other takes 53 liters, you just put them together for 154 total liters. Now, given this all, we've now completed our map. We've been over at volume. We've been at mass and particles. So now, as long as I have an amount in liters and it is at STP, standard temperature and pressure, I can go over to moles. And from there, I can count mass or I can count particles. Basically, think of this as your roadmap, right? And you want to start somewhere and end up somewhere else. We just went over how to do volume, going back to moles and moles to volume. You can go back and review those if you need. Now I'm going to do a couple of examples where it's going to end up going through two paths. We could go from particles to volume, or mass to volume, or particles to mass. There's all sorts of combinations in here. So this one says how many atoms are in 2.24 liters. So we know we need to go to atoms. I can highlight that. Hey, look at that. And I know I have 2.24 liters. And not always, but sometimes it is significant that we're dealing with CF4. In this case, since we're looking at F, that is going to make a difference. So let's plan out our path here. Let's make a plan. Let's look at the diagram that we just had. We're going to go from atoms, which we're in particles at this point, right down here, and we want to end up with atoms. Or yeah, no, we're in volume. Excuse me, we're in 2.24 liters, and we want to go to atoms. So we want to get from volume to particles. Now you see there's no line. We have to go through the mole. So to diagram this out, I'm going to go from volume to moles, and then I'm going to go from moles to particles. So it's going to be two fence posts. So let's go through and do that. Start with 2.24 liters. Put it into a fence post. Liters will go on the bottom. That's 22.4 in 1 mole. Notice how 1 has always stuck with mole this entire time. Then I'm going to do a second fence post because I have a second step. That will only get me to moles. The next fence post will get me to particles. And you can do this all as one big fence post or two separate ones if you'd like. Could I go from moles to particles? Moles is going to need to cancel out, and I'm going to go to molecules on top. So the math works out 22.24 divided by 22.4 times 6.02 times 10 to the 23rd, which is 6.02 times 10 to the 22nd. Now, that kind of makes sense because we had a tenth of the molar volume, right? The decimals just moved over, so we ended up with 1 less power of 10 on Avogadro's number. But there is one caveat here. It said atoms of F. And since there are 4 atoms of fluorine in CF4, you can see a CF4 molecule, there's 4 atoms in there. We need to take that 6.02 times 10 to the 22nd and multiply it by 4 to count all of the fluorine atoms. And when we do that, we get 2.41 times 10 to the 23rd atoms of fluorine in that 2.24 liters of carbon tetrafluoride. So, as long as you plan everything out, you should be okay. We started in volume, went to moles, went from moles to particles. So, in doing that, we need to keep in track of the 4 fluorines in CF4 and just multiply our answer by 4 at the end. One more example, I think this is our last one. How much space in liters does 1 gram of helium occupy? And it does say at STP. That's important. That lets us know that we can use our 22.4. But not right away, because we need to plan this out. What are we in? Not particles, not volume, but mass. We start in mass. So we're going to go from 1 gram to how many moles that is, and then from how many moles that is to what volume, in order to answer the question, which is how much space. So let's start with that 1 gram of helium and convert those grams to moles, like our first arrow here in our map. That way, 4 grams of helium goes on bottom. I got that 4 from the periodic table. It goes under 1 mole. And then a second fence post, that will bring us from moles to liters. So all that ends up doing is taking 1 divided by 4 times 22.4, which is 5.6. And we now know how much volume we need for 1 gram of helium. Obviously, it's quite light, and 5 liters is not that whole much. I always imagine liters by the 2-liter bottle. That usually gives me a good idea of how big it is.